Hi guys, welcome to another wonderful video of mine. This is Mosdi Academy Physics channel, and today again, as usual, we are looking into the sound wave and the longitudinal waves, which you have studied in your junior classes about wave concept. And if you are new to this channel, you can actually consider subscribing to the channel. Then if you are the type that you are doing an A-level exam, this my short method of taking concept one by one is one of the best way to get in there. So you watch them in series, concept video on mechanisms, on light, on heat, and so on and so forth, are available right on this channel. To go to the business of the day, I believe you have somewhat a pre-knowledge about types of waves and some other things you might have studied before in your early classes. So having said that, let us delve into the work of today. The work of today, I'm going to be talking about basically about the sound waves and which is an example of longitudinal wave, that is a wave in which the direction of traveling is the same as the propagation of medium. That is just the definition. I'm not going to that, but in today I'm only focusing on some factors that affect speed of sound, and I'm going to do two examples based on O-level question and derivation based on A-level question. So doing that very quickly, we can start with that. Now, based on the propagation of sound, there are some factors that affect the speed of sound. In junior classes, we might have studied that sound wave are formed as a result of compression and rarefaction, that is compression and expansion. So having said that, I said waves are sound waves. You can say sound wave, basically, I don't want to waste that time. You can say sound waves depends on, let's just put it in this format so that you make more sense. One can say temperature of sound. Temperature. Now, the speed of sound, that is the speed at which sound travels. Your sound, you all know, require material media. That should have been taught in junior classes, is temperature. So temperature is one of the factors. Then two, we talk about elasticity of medium. So now, I want to focus on these two and give you some good example on how Laplace and Newton actually explained this process and some questions related to them from your pack. So this is what I want to do in this video. So the first one is, how does speed of sound affect how does sound, how does it vary with temperature? From junior classes, we say the speed of sound is directly proportional to the square root of temperature. So just like this, speed of sound I'm writing as Vs and T as the temperature. So here we can say, okay, if the media are more than one and the speed is changing from one form to another, please don't step on bike. If the media are more than one and the speed is changing from one place to another, and then the speed of sound is equals to, there will be a constant, that is K under root of T. So if I make the K sort of formula, the first thing I'll talk about here, it will be speed of sound divided by square root of temperature. So this is the constant parameter we use in junior classes. So therefore, you can now say therefore that here, if the speed are more than one, we can say the first speed of sound over the second speed of sound is equals to the square root of the temperature of the first one over that of the second. And that is the relationship. Some of you can say V1 over root T1 is equals to V2 over root T2. So this is still the same thing as what I've written there. So the first formula you are going to keep in mind, which I think we are going to use to solve some questions from JAM, and I think most questions today was from JAM according to my admin. I'm not sure about where they pick question, but I asked them to pick O-level question for you guys to see the importance of all these things we are doing. So this is the first formula, and please you can keep it in mind to relate speed of sound with respect to temperature. We use this simple formula. Now, having said that, elasticity of the medium, that is another factor that affects the speed of sound, and that is the second thing I would love to talk about. Then before that, I would actually love to change my ink color maybe to blue. So about the elasticity of medium, we need to understand. We also said, this is point 2, the speed of sound is also said to be proportional to the square root of, let's say, the elasticity of the medium over its density, which is rho. I hope students have studied that density is rho, and this is where we are going because it's very important to understand something. Now, when we talk about elasticity of the medium, which I've written in E, elasticity of the medium depend on different factors. So when we talk about different factors, you need to keep a lot of things in mind. That's why I'm not rushing. Now, elasticity of the medium, now, we can say elasticity of solid. When we refer to solid, elasticity of solids. Let me face. So when we talk about elasticity of solid, we talk about a constant we call Young modulus. And that is why I said you need to keep a lot of things in mind from junior classes. But when we talk about elasticity of liquid and gas, of liquids and gases, we talk about what we call the bulk modulus. So these two things are going to be used when we are solving questions. It's important we keep this at the back of mind. Elasticity of the medium is E, whereby that is when it is solid, it is Young modulus, which is a stress over strain from junior classes. If you still remember that, maybe I put that here before I move forward. When you say Young modulus, which we denote by E most time, or some people use Y, something like gamma, is equals to stress, tensile stress over strain. Keep it in mind. In some, especially those doing IGMB, which is the next exam for the A-level student in Nigeria. So the next one is bulk modulus. I write that one as P is equals to change in pressure, that's a P, over change in volume, that's a V over V. So these two are also important from your study of which topic do we even do this? That is under the topic of elasticity, if I'm not mistaken. Under your MEC next time, you will have studied that. Videos are available on different type of modulus, shear modulus and bulk modulus, for those that are beginners. So the truth about this formula is that the formula can be interchanged, since we know it is elasticity over this. If it is solid, we define solid in terms of Young. If it is liquid and gases, we define in terms of bulk modulus. And these are the formulas which you need to keep in mind. So because of this, the direction in which sand propagates in medium depends on some thermodynamic properties. And that is where we are going, my dear student. Because the direction depends on thermodynamic properties, we are going to consider the two formulas given by two different scientists that are very popular. That is Newton definition and the other one we call Laplace definition. That's exactly what we want to do. Note the first one, no argument about that. But when it comes to bulk modulus of elasticity, that's when we are considering liquid and gas, the formula we have here will change because we say it depends on thermodynamic property as sand is being propagated through liquids and gases. So in that sequence, admin will minimize this for me and give me one free page. So admin, please minimize the page for me. And thank you very much. I need a plus page. Thank you, admin. God bless you. Now, in sequence, please make it full back. In sequence, I'm going to move on to the next one. And if I want to do that, what I'm going to do now is just to actually prove both Newton formula and what the Laplace formula. Now, according to Newton, Newton said the speed of sand in air is an adiabatic process. Is an isothermal process. When I say isothermal, my dear student, what I mean by isothermal is that it does not change. The temperature is constant. Isothermal, the same temperature. So Laplace said the speed of sand is an adiabatic process. All these processes are polytropic processes we've done in thermodynamics. If you are new to my video online, please you can search for thermodynamic process and watch the concept video from A to Z. It is just within 3 to 4 hours you are going to know all what is necessary to know under that topic. Now, having said that, I want to quickly prove in sequence to what we have learned. Now, we said the first one according to Newton. Now, Newton formula now. That's a Newton formula. Newton proposed that speed of sand is an isothermal. That is, its temperature remain constant as what? Speed travel. So if temperature remain constant, from your formula, you know there are three thermodynamic processes. I'm not supposed to be teaching this. I have an example to do. That means I'm increasing my pace now. I hope you understand. So according to Newton, that means pressure, volume, temperature are three thermodynamic properties or processes you explain. So if temperature is constant, you call that what? Boyle's law. I hope I'm communicating. Boyle's law tells you that what? Pressure and volumes are inversely but related. So if it is an isothermal process, obeying that law, we are going to say, what is Boyle's law? That is PV is equals to what? Constant, which is K. This is Boyle's law. Everybody knows that pressure is inverse proportional to volume. So let's differentiate this. If we differentiate this, I'm using the product rule of differentiation. For those who don't know, just listen. This will be PdV plus VdP is equals to 0. I have used product rule of differentiation. That is VdUds plus UdVds. Please, I'm not explaining because of time too much. Just listen up, because if you're an A-level student, you can be asked to prove. So on this one, what I want to use is I want to make the P subject formula. On doing this, I can go that PdV is equals to negative VdP. I hope students can see this. On simplifying, the P equals to, you can say negative P over V dV. So that is that about this. Then remember that we said in continuation that the speed of sound in liquids and gas is given as a result of, remember I said it is defined in terms of what? Bulk modulus. So before I go into this, maybe I should just try and do something so that everybody can see. Now we say bulk modulus was defined as a change in pressure, data P over volume change, excess pressure over change in volume, data V over V. This is the formula we use for bulk modulus. So from here, what do you see? What is dP? Change in pressure. Now, data P is simple as dP. Maybe I should be using data P for dP. It's the same thing. So if I substitute here, I'm going to have, so the formula is always having negative sign. We've done that under the topic of elasticity. Please, you can watch that. But if you don't know it, there's always a first time to everything. So if we substitute dP, where we see data P as dP, we are going to cancel out. A lot of things we cancel out. So we say the bulk modulus is nothing but equal. Minus will get cancelled out. As you can see, it should be plus. Substitute, when you see dP as a minus P over V, this and this will get cancelled out. The only thing you are left with is just but what? But P. That is what you are going to have left after substituting this value for data P. So now, having said that, remember we said that the speed of sound is equals to square root of bulk modulus is now equals to pressure over, then that one is equals to density. Remember the formula, it is E over P. E can be Young modulus and it can be what? Bulk modulus. If it is bulk modulus, this is the formula for bulk modulus. According to Newton, this is the formula for the P. We substituted here, we got P. So P is pressure, rho is what? Density. That is the first. Now, if we now put this as a parameter, now the pressure of a gas at normal temperature and pressure, we call it at NTP. The pressure of a gas is 1.01 times 10 to the power 5 Pascal or kilogram per meter, what do you call Newton per meter square. Yeah, Newton per meter. My students are here, thank you very much. They are doing well. Now, then you also have rho. Rho is density. Density is 1.293 kilogram per meter cube. Substitute that here to get the speed of sound. Now, if you put that is 1.01 times 10 to the power 5 divided by 1.293 square root. The speed of sound will give you an approximate value. I want to change my marker for understanding. It will give you an approximate value about 279.8 meters per second, which is not correct to the constant that we take for what? The speed of sound experimentally. Everybody knows speed of sound is about, from experiment, is about 330 meter to 340. Most of your textbook with it. So that is why, according to Newton formula was said to be what? To be wrong. But why am I doing this? Because some question will test you about calculating the speed of sound. They only give you pressure and density. Just go for square root of pressure over density, which is what? According to uniform, but it is not experimentally correct. So we said sand is not an isothermal process. So the correction was made later in the year by a scientist called Laplace. In sequence, my dear admin, please minimize this, give me a new page to explain Laplace formula. Let's see that before we go to. Thank you very much. Thank you. Now, if we want to look to the next one, which we call Laplace approach or Laplace explanation with respect to that, we can say according to Laplace approach. Now, Laplace introduction or explanation to the speed of sound is quite different because Laplace treated the speed of sound as being what we say Laplace correction now. Laplace correction. Please, so to speed of sound. He said speed of sound is adiabatic process. Isothermal means constant temperature. Adiabatic means what? There is no change in it. That is, Q is equals to 0. We've done that under the concept of thermodynamics. For those that are just joining us on this page, you can check that out if you still want to learn more about what we're talking about. So Laplace was able to tell us that it's an adiabatic because he said sound travel as a result of what? When the air molecule travels, they are either what? They can be compressed and they can expand. So the heat is being lost and heat is also being gained. So there is a kind of counterbalance. I don't know if you understand. The simple layman language I can give to you is what I'm trying to do now. So there's a kind of counterbalance between heat compress and expand. So air molecule is compressed and they can also expand. So the amount of heat gain is equal to an amount of heat loss. So therefore there is no heat that is lost. And according to adiabatic process, when Q is equals to 0, we say all we use from derivation is PV raised to power gamma is equals to this constant. PV raised to power gamma, whereby gamma is molar specific heat. Watch the concept video, you are going to understand. So this is the interpretation we give to that. Let's differentiate, just like what we did in the other one. So differentiating this one, I am using product rule to also differentiate. Don't sleep on bike. We have using product rule. This is a PdV plus, look at this. I'll use the normal, if you have a raised to power n in differentiation, it is what? N a raised to power n minus 1. I hope you guys know if I give you x squared, 2 minus 1, whatever. I want to do the same thing to v raised to power gamma. So P dv, I'm taking P as a constant plus, look at what I'm doing, guys. You know, U dv ds, P is constant. So I have P, then if P is constant, dv, then, oh wow, don't let me make mistakes so that will you be able to understand this. Oh, let that please come up, thank you. Now, this is U, this is V. So I'm just doing that. If this is U, you differentiate B. If this is, then you pick the second one, you differentiate the other one. So this is my U, this is my, U dv ds. So that's what I want to do now. Let me change to your right to understand. So this will be P, then here, if I differentiate this one, it will be open bracket. This one will be just like this guy. On top we come to know this is gamma V. This is gamma V, gamma minus 1 dv. Then close bracket plus, then I have V raised to power, that is dp. I can also say V raised to power gamma is constant. When I differentiate P, it's going to give me what? dp. I've only used is equals to 0. So now I will cancel out, no need to waste time. V raised to power gamma, we cancel out V raised to power gamma. I've used the knowledge of your indices, you can try that out. So now I can say P, I have this is gamma, P gamma dv plus dp is equals to 0. So guys, you can check what I've done that. What I've done there is just a simple mere differentiation using the product rule. So if you have issues with all this one, I don't think you should you can check our introduction to physics stuff. I've done some basic rule. My admit, your eye is very red. I don't know if you want to sleep, you can go and sleep. So, but notwithstanding, what I'm after is for you guys to understand what I'm actually doing here. So if you make the P square formula directly, we can say, yeah, you should go to the other side to be P now this should be gamma minus 1. Gamma minus 1. So it should be P over, this should be P, this is gamma minus 1. Because I have gamma raised to power minus 1. So it should be P, this is gamma raised to power minus 1. So directly, I don't want to waste time so that we can get our final answer. You know the formula is the speed of sound Vs is equals to square root of the elasticity over the density. So we are talking about liquid and gases. If we talk about liquid and gases, we are talking about bulk modulus. And because we are talking about bulk modulus, remember bulk modulus formula is change in pressure, delta P, I should have written the P over delta V over V. So what I'll just do here, my dear student, is just to substitute the value of this one. And if I substitute the value of this one from here, I will make the P square formula just like what I did at the other time. I should be having, yes, very correct. Yeah, I should be having, now I should be having, this is P dV over gamma. See, if I move this one to the other side, this is what I want to do now for you guys to see. What I'm trying to do here is that this is something saying P, something raised to power minus 1 is 1 over that thing. P over gamma, then dV is equals to negative dP. That's what I'm having from here. Remember the formula has negative, just like what I did the other time. So if I substitute that, I'm going to have B is equals to put all these things back as dP here. So minus cancel out, everything here will cancel out each other. So what you are going to have is, I'm going to have what left is gamma P. I think, yes, gamma will remain, definitely gamma P. So that is what we are going to have left. So if gamma P is left, so our formula is this, so the speed of sound is now equals to square root of gamma P over, that's where we are going, over density. So now, we now substitute to get, this is the formula of Laplace, which was the correction to Newton's law. And if we put the value of each of them, I think gamma is 1.42 at admin. So gamma, molar specific for the gas, is 1.42 at NTP. So if gamma is that, we know the value of rho, we know the value of P. 1.0 whatever times 0. 1.01 times 10 to the power 5. And this one is 1.293. So substitute that. If you substitute this and press it on your calculator, this will give you 336 meters per second. So this is said to be what? Experimentally correct. So there are two formulas you need to keep in mind now. Speed of sound is equals to pressure over density, and speed of sound is equals to what? Gamma pressure over density, all in what? Square root. Those two formulas are important even if you're in 100 level, because examiner will test you on this. So it depends on the parameter given to actually know how to work on it. So this is acceptable because it's what? Almost correct. Experimentally. So please keep that at the back of your mind. Very, very important. So P is pressure and this guy is density. Density is 1.293 kilogram per meter cube. And when you put that value, taking the square root, you have about 336. So these are the two formulas and these are the two approaches according to Newton and Laplace. Laplace is more correct. So speed of sound in here does not depend on pressure only as a single factor, but depends on temperature as a single factor. We've talked about that at the beginning of the class. So now I'm going to stop here, but before I go, I'm going to do two questions. I'll leave the third one for you guys to do. So admin, please, to the question. Thank you very much. Now the first one is extracted from 2013 question 27. Please, this is UTME for UTME students. You can always keep that in mind. Now, the question says, what is the velocity of sound at this temperature 100 if the velocity of sound at 0 degrees Celsius is 340? So we are calculating the relationship we give about velocity of sound with respect to temperature. If you don't forget, my dear student, is that I don't like that. Apologies. That's one thing about me. Now is that the velocity of sound is proportional to square root of temperature. I believe you can recall that. So if you go by that, solution-wise, I'm going to say solution. So directly we can say from our formula V1 over V2 is equals to square root of, I told you to keep it in mind, T1 over T2. So directly, nothing to solve. So just parameter-wise, and again, under normal temperature and pressure. Very important. Normal temperature. What's the normal temperature formula? Kelvin, not degree Celsius. That's the only technicality there. So I convert this directly. This will be 373 Kelvin. I hope students remember that. And this one will be 273 Kelvin. 0 degrees Celsius is 273. Now, when you're looking for the velocity of sound at 100, if the one at 0, 0 will be the first one. So if V1 is, what's V1? 340. So I'm going with this. Continuation from here. 340. I'm looking for the new speed is equals to square root of the temperature at 340 is 273. And we calculator, please note, and divided by this is 373. So it's all about understanding. I don't want to square any both sides. Like I said, to remove square root, square both sides, but no time. So just admit we just going to divide 273 divided by 373. Then this will be 340 over V2 is equals to, admit can give me calculator. Thank you very much. So this is a thank you very much. What you make my work to be faster. 0.73190. So now, I will take square root of this. So I'll take square root directly because calculator is allowed. So if I go by square root of, I don't know, maybe the square root of my answer. So I'm having 0 points. This guy is giving me 0.8551 and so on and so forth. So I'll cross multiply, I'll multiply by 340. So multiply the answer by 340 will be the answer. So V2 approximately is 290.8 meters per second. So you check the option. So that's what you are going to look for. That's what I'm having, 290, and none of the option here is correct. So I think maybe there's a mistake somewhere which I don't know. I can check it for the last time. What is the velocity of sound at 100? The velocity of sound at 0. Velocity of sound at 0 is 340. I hope this is 340. 0 is 340, 273, 373. So 340 over V2 is then first temperature. I'm taking this one over 3. Yeah, I'm very correct. This is 0 point. Let me press that myself. So I think there is a typo error somewhere. 273 divided by 373 is 0.738. Admin is very correct. Then square root of that, square root of the answer, 0.8551 multiplied by 340. 340. So 290.8 is the correct answer to this question. I don't want to waste my time on that. That's very correct. Next one, please. Next one, 290 is the correct answer. So the next one says that, given that Young modulus of, very good. I love this. Given that Young modulus of aluminium. Now, aluminium is a what? It's a solid. So it's still very simple. At solid, we define what? Young modulus. At liquid and gases, we use the bulk modulus. So this is very simple. So we can just say the density is this one, the Young modulus is this. The speed of sound, directly, no time to waste time, is square root of Young modulus over what? The density. So Young modulus directly, that's it. If it is bulk modulus now, we are going to use pressure over density. If it is Newton formula, or gamma pressure over density. Please don't make mistakes. So Young modulus was given. Sometimes if Young modulus is not given, they can give you stress and strain. You divide stress by the strain. So directly is just the direct solution. So what is the Young modulus? E was given as 7. I hope this is raised to power 10 times 10 raised to power 10. I don't even have time to be checking. And this is on 2.7 times 10 raised to power 3. Everything is in square root. So I think this one is a direct thing. 10 minus 3 is 7. Square root of 7, that is 3. So 7 over this one square root, that's 5.1. Anything 5.1 here? Yes. Times 10 raised to power 3, absolutely correct. Meters per second. You can confirm it with your calculator. This should be the right answer to this. And this is what's carved out from 2003, question 19. So anyhow you want to do it, you shall make sure you what, can you speak that language? You make sure you what, you punch your calculator, put the parameters there, then you will be able to get the answer. Like I said, there are 3 questions. The third question admin will be an assignment or a form of illustration which you are going to attempt. It will not be an assignment because you are not in the classroom. Attempt this. There is a question based on what we just taught now. So speed of sound and temperature. Just the pressure has no any impact on it. So guys, this is where I'm going to stop for this video. I'm going to see you soon in my upcoming video. Maybe I'll still do some questions, not on this, another thing which will be in a short video. If you find our video interesting, you can consider subscribing to the channel. See you soon and do have a wonderful time. Bye bye. How many minutes?